And again, this is a very important, very interesting material, and very fundamental. It's called fundamental metrics. So every field has fundamental metrics. So computer vision fundamental metrics you are going to learn now. And so this is in a bigger context of the transformation between two images. So we have talked about in great detail, transformation can be just translation. One image is translated from compared to other image. It can be rotation. It can be rigid, which contains both the rotation and translation. It can be similarity transformation, which compares the scale and the rotation. And affine, which has 6 parameters. Projective, which has 8 parameters. And pseudo perspective, which is approximation of the projective. And then we have bilinear, and so on. So the whole series of transformation we have gone through, and you know how we achieve them, and then we have used them to align images and so on. Okay, so now this is in that context. So we're going to talk about fundamental metrics. It's a little different, but it's very interesting, very important part of computer vision. So once we know how to compute fundamental metrics between two images, then we can use this for stereo, we can use for structure for motion, we can use for view invariant action recognition, and many, many applications. So here's application of stereo. So we have two images, and in order to find the depth disparity, identify these images so that we can just take a pixel from this row and go to the same row and find its match. And this will become the depth map, and you need to do that using fundamental metrics. So this is the problem, that you can take images from any different orientation, but you want to flatten them like this so that you can go from one row to the exactly same row and find its match. You listened to this one before. I will not turn on the thing. So somehow this, when I just enter, it works, and then it doesn't work. Anyway, so you have listened to this Photosynth video from Microsoft, which shows you that which shows you that you can compute taking the cloud of points, you can reconstruct 3D and so on. So fundamental metrics it was introduced by Longent Higgins, he's a British researcher, 1981, and he actually introduced as an essential metrics, and we are going to talk about that. And he had a paper in Nature, which is a very prestigious journal, as you know. Then 1992, simultaneously, Richard Hartley and Olivia Fogeras, they came up with the fundamental metrics. So essential metrics is basically relating the 3D coordinates and of two images, and the fundamental metrics relating the image coordinates of those 3D points. So that's why it's called fundamental metrics. And we're going to talk about Zhang Yu Zheng's efficient method to compute, the robust method to compute the fundamental metrics. And we will also talk about Hartley's method, the 8-point algorithm, to compute the fundamental metrics. So first we apply this, and we'll apply this. And so Zhang Yu Zheng was a PhD student under Fogeras. So all these guys are somehow related. So the fundamental metrics is so important that there is actually a song on that. So I will play for you to just motivate you to there's a lot of fun in science also. And this is a link for that, and you can watch the rest of the one. So maybe the network is slow or something. Or do they bend to see the videos and the UCF network? You just wait a little bit.
Doesn't seem to be loading.
No?
Maybe it's stuff at all. 1 second, maybe refresh.
Yeah,
It's loading, is it?
Yeah, maybe refresh.
well, there's now.
But I play this at home. Okay. Good. So where is the sound?
It's playing. You paused it earlier.
It's playing now?
Yes.
Okay, is everyone ready? Yes, yes.
So that's a book by Zissamin and Andrew Zissamin and Hartley. It's a very famous book.
The fundamental matrix used in stereo geometry. A matrix with 9 entries. It's square with size 3 by 3. Has 7 degrees of freedom. It has a rank efficiency. It's only of rank 2. Call the matrix F and you'll see 2 points that correspond. Column vectors called x and x prime. X prime transpose times f times x equals 0 every time. The epipolar constraint involves epipolar lines. Those multiplying f by x results in vector L prime. It's the epipolar line. The other two passing through x prime. A 3-component vector of homogeneous design. The left and right null spaces of F are the epipoles E prime and B. All of the epipolar lines should pass through these. Is a linear estimation example 10%, 8.7. Construct a matrix, take the SPE and the elements of F in the last column of B.
These are edges. Yeah, shift points.
If you try to estimate F with a coplanar set of points, your sample set will be degenerate and will not bring you joy. When doing the estimation, if you don't perform rank deprivation, your epipolar lines and the epipoles will not coincide. But if your scene has 3 views, the trifocal tensor is what you use. Constraints from the third view, hash like blue, hash has been determined. Just 2 views.
So it's nice. Huh? Okay.
How did you find that?
I try very hard to entertain you guys. Okay, so let's now get serious to talk about what this fundamental matrix is, and we will first talk about some background preliminaries so that you feel more comfortable, because always hear people say, well, I don't know this math and I don't know this. So let's cover this. So we are going to talk about the concept what is called linear independence, and we'll talk about rank of a matrix. As you heard, they were talking about rank in that song, and matrix norm, singular value decomposition, and vector cross product, which can be expressed in matrix multiplication, and other thing is called RANSAC, which is the random sampling and consensus. Again, I have a song for this, so I'll play for that. And that's also very, very important technique which is used in many, many different things. And you should understand that. Okay, so linearly independence. Okay, so this is a very fundamental concepts. And so we have a set of vectors. These are shown here, n vectors. We will say that these vectors are linearly dependent. Then if we can write down like this as a linear combination of these n vectors, and this becomes 0, such that not all the elements are 0. If the elements are 0, that's fine. But if all the elements are 0, not 0, then these are called linearly dependent. They depend on each other, which means if it is 0, then we can take one of the element which is not 0 and express that in terms of other rest of the n minus 1 elements. So the vectors which cannot be written like this, or if they can be written like this, then not all are 0. They are called linearly independent. If not all of them are 0, then they are called linearly dependent. Okay, so that's the idea, that these are the unique vectors, so that I cannot express another vector. I can express another vector in terms of those two vectors. Like when you have two dimension, you have x-axis, y-axis. So x-axis says 1, 0, y-axis 0, 1. Now I can represent any vector as a linear combination of those two linearly independent vectors. And they can be, like this and like that. Again, they are linearly independent. But if I take the vectors such that, which cannot be written like this, then we will have one of the vector will be linearly dependent, and we want to find out what are the maximum number of vectors which are linearly dependent, and that is important concept. So another thing is the rank of a matrix. So matrix, as you know, has a columns and rows, and then we are saying matrix will have a column rank and the row rank. And this is valid also for the rectangular matrix, which is not necessarily a square matrix. So column rank of a matrix is the maximum number of linearly independent column vectors. So if you have matrix with many columns, now some columns may be linearly dependent on other ones, but there can be very few columns which are linearly independent, that none of those can be written as a combination of the other ones. But when it's linearly dependent, then some of them can be represented linear combination of the remaining one. So that's the idea. And the row rank is again that we take the rows, how many rows we have which are linearly independent, that will come row rank of the matrix. And now once we know the rank, so that will give us a dimension of that matrix. That maximum dimension we need is this much to represent all the vectors in that space. So we have a column rank and we have a row rank and so on. So let's look at simple matrix. This is the 3 by 3 matrix, and this has 3 rows and 3 columns. So maximum it can have 3 linearly independent vectors, linearly independent columns or linearly independent rows. But let's find out how many are there. So one way to show that, to convert this into upper triangular matrix, which means on the diagonal, below the diagonal, we want to make all 0, and above the diagonal will be non-zero. So we want to make this element 0. What we're going to do, multiply this with 2, and we add up till it becomes 0. So that is operation is called here, that we multiply 2 with first row and add with second row, and that will become 0, 1, 3, because 2 minus 2 is 0, and 4 minus 3 is 1, and 2 plus 1 is 3. And then we want to make this also 0, so that we can do the same thing, multiply the upper one by 3 and subtract that from the third row, and that will give us, this will become 0, because 3 minus 3 is 0, and 6 minus 5 is, 5 minus 6 is minus 1, and similarly this will become 0 minus 3 is minus 3. So now we have, in this column we have all 0, and in this column below the diagonal we'll make this 0 also. So we'll multiply again with the row which is shown here, the R2, we can just add them. We can add this and this will become 0, and this will become 0, and this is what we have. So now all the elements below the diagonal, first column 0, all the elements below the diagonal, second column 0, and third column 0. So this is called upper triangular matrix. It has non-zero element in the upper triangular, 0 element on below lower triangular. It's called also a row echelon form. So now as you see that this has actually 2 rows which are linearly independent, because this is 0 rows, 0 columns, so it's not, it can be always written like that. So that is one notion of the rank of this matrix. So the rank is 2, okay, instead of, even though it's a 3 by 3 matrix. So that's what we have. Now next concept is called singular value decomposition, which is called SVD. It's also very useful. And there's a whole theorem which is saying that if you take m by n matrix A, for which say m is greater than or equal to n, we can write that matrix in terms of these 3 matrices. Okay, O1, sigma, O2, and this is the factorization of this matrix into 3 matrices. It's called singular value decomposition also. Okay, so this is m by n, and this O1 will become m by n, this sigma will become n by n, and then O2 will become n by n. So if you multiply this, will get you m by n, and multiply with this again n by n. So so this sigma is diagonal matrix which will have the singular value. Diagonal matrix means only the diagonal elements are non-zero, other elements are 0. Okay, and so these matrices are orthogonal. Okay, so we talk about orthogonal matrices in the rotation matrices. Okay, so which means that their property that we can find the inverse of the matrix, just find a transpose of that will become inverse for the O1 and O2. So then we talk about a norm of a matrix. Norm is like absolute value. If you take a element, take a vector, you can find the magnitude of that. And magnitude is, if vector is 2 dimensions, say x and y, so x squared plus y squared under root, that's called Euclidean norm. Or you can take absolute value and them up, which is, L1 norm and so on. So therefore, similarly, we have the matrix, because matrix has different elements. It's not just vector, but there are many rows. So the L1 norm is obtained by taking the value of particular particular element in a column, and we take the absolute value, sum them up, and we get the one value for a column. Then we take the next column, then we will get the value in next column and so on. So here, as you see, we're looking at different columns. Columns is the second index here. First index is row. So we get different, one value which is sum of absolute value of all the elements in that particular column, and then we pick the maximum of that. That's called L1 norm of this matrix. And there's L infinity norm, which is that you are taking the maximum or the sum. So here we are going through different rows, here we are changing the column and going through the different rows, and then added up is called L infinity norm. So these notions will be useful, because once you feel comfortable what we are talking about, then we can understand this whole thing. The last thing in this is what is called the vector cross product that can be expressed in the matrix multiplication. So two vectors A and B, how to find a cross product of that. You have learned this in physics. So the way to do it is you took I, J, K, and this is the first vector, this is the second vector, and find the determinant of that. Yeah? So you say, you take this one, multiply with this, subtract this is the first element, minus, then take one, multiply this and subtract that and this one, and then this one, multiply this with this, and you get this one. This is the cross product of two vectors, which is very simple. Now the question is that we can do the cross product using the matrix multiplication. So we have this vector, the B vector. From the A vector we will find this anti-symmetric matrix. Okay, so anti-symmetric matrix is that you look at a diagonal, then these elements are negative. This is negative of this, this is negative of this, this is negative of this. If this was positive, then it's called symmetric. On the diagonal, elements are same, but now they are just different signs, and that's called anti-symmetric matrix. So we take the vector A, make a matrix like this, 3 by 3 matrix like that, anti-symmetric matrix. Now we multiply with this vector B, then we are going to get from here 0, then minus BYAZ plus BZAY, which is this term. From here we'll get BXAZ, and this will become 0, and then the BY will become 0, and this will become minus BZAX, which is this one. Then this multiplied by this will be BXAY with minus sign, and BYAX plus sign, which is this one. So this is exactly same as this. So we're saying that you can express the cross product with the matrix multiplication, and matrix is obtained anti-symmetric from the first vector. So we're going to use that. Okay, so next thing we are going to talk about, and we have discussed this a little bit, but we can again review that, and I have a song for you for this also. And so let's say we want to do least square fit. So we have a bunch of points, and we want to find the line, baseline going through that. And we have talked about least square fit, which is the over constraint, that we have more equation always and less unknowns, as we did Lucas Canarde, we did affine transformation and all this thing. That is least square fit. And when we want to fit a straight line, we'll have many points. A straight line has two unknowns, but we can get 100 points, and we want to fit the line. So each point will give you the one equation. So we have 100 equations, and we have two unknowns. So it's called over constraint system. We have more constraints than unknowns, and we always use least square for that. The second thing, which is RANSAC, which is called random sampling and consensus. So let's say you have 100 points. Now, to find the parameter of a line, you just need 2 points, but you don't know which 2 points. It's because in those 100 points, there may be lots of outliers, some wrong points, and you will have problem. So what you do, you randomly select or sample 2 points from 100 points and fit a line, and then find the error of that line from other points and note down that. Then you randomly select another 2 points, fit a line, find the error, note down. And you keep doing that, so you'll have many possible lines. You will pick the line which give you the least error. Basically that's called RANSAC, and it's very intuitive and very simple and works very powerful. So we're going to talk about that. Then there's another interesting thing, which is called under constraints, called Huff transform. So Huff transform actually will take fewer constraints than required and find all possible solution, and then do the voting. So we have these three levels, it's under constraint, equal number of constraint, what you are unknown, and this over constraint. So all these three are very important methods which we will be using in computer vision. We already talked about a lot about this. We're going to talk about this today, and this we'll talk. There's a whole lecture on Huff transform. We'll talk about that. Okay. So this is the problem that we have set up points. So let's say if we have 5 points, we want to fit a line to that, and the equation of line is y is equal to mx plus c. Fitting a line means we want to find m and c, the slope and intercepts. Okay, so which means that standard linear are that we want to, if we know that which points belongs to the line, if there's only one line, then it's easy. Then we can just do the least square fit. If there's only one line, and this is the equation of a line, and we will basically find m and c such that this error is minimized, which is take the error, square the error, minimize that. That's called least square fit. Okay, and as we have been doing, we will find derivative of this with respect to m, derivative of this with respect to c equal to 0, and all those things we have done many times. So which is shown here. So another way to do is using pseudo inverse, but they will end up with the same solution. That we have each point we get one equation, we get a bunch of equations, n points, n equations. We put them in this matrix form. That if I take this one, multiply with first row, I'll get first equation, take this and multiply with second row, and all this. This is a different way to write these equations. Then this matrix cannot be inverted, so we'll multiply with the transpose, and then the whole thing will be common, and this will become D. So that's that's what we have been doing many times. So you should know that. And this kind of question will be on exam, so you should be prepared. Okay, now let's talk about what is RANSAC and why is it good, and So RANSAC, as I said, is called random sampling and consensus. And let's go to the song first.
When you have outliers, you may face much frustration. When you have outliers, you may face much frustration. If you include them in a model fitting operation. If you include them in a model fitting operation. The ones fit to a sample set of minimal size. The probability of the set being as one was testable set equals computation of was testable set equals computational constipation. In random samples, we provide an example. Each random false would have its own unique sample set. Each random false would have its own unique sample set. And make sure that the sets you choose are not degenerate. And make sure that the sets you choose are not degenerate. And the number of sets to choose is based on probability. And the number of sets to choose is based on probability. Updating n as you go minimize such that it's not updating n as you go we minimize. So if you gamble, so if you gamble,
in this, as they say, notion of inlier and outliers. So simply inliers are the points which lie on the line, Outliers are the which don't lie on the line, which can be due to noise and so on. So a priori we don't know which are inlier, which are outlier, and that's the way we are going to pick these randomly and look at these lines. Okay, so let's, this is the algorithm. It's very simple, 2 steps. Randomly select 2 points to fit a line. Find the error between the estimate solution to all other points. If the error is less than tolerance, then quit, else go to step 1. You just keep going that and you will be done. So now we are going to use these concepts, the RANSEC, the rank concepts, linearly independent, SVD, and all those things to talk about how we can compute the fundamental matrix between 2 images. Given 2 images, we're going to compute the metrics which relate these 2 images. So we're going to also talk about what is called epipolar geometry, as you heard in the song, the first one. So let's say we have a 3D world, like this room here, and we take 2 pictures. One is from left camera, another one from the right camera. So left camera will give you this image plane, and then right camera will give you another image plane. Okay. So now, as you know, that if there's a point in 3D here, its image will be formed here. This is the image plane, and this is the lens of a camera, center, and let's say its picture is XL. And of course, all the points which lie on this line will have the same image. And similarly, the image of this point, same point, in this will be this one, but the other points will have these different images because you are looking at different side. Okay. So now we are going to assume that these cameras are separated by T translation vector, and so these points which form a line, which is the projection of actually one point, which is the image of this point, this 3D point and all the points here, it's called epipolar line. Okay, this is called epipolar line. So what is happening, that point in left image maps to a line in the second image, because all the points here are mapped to one point, but when you look at from different side, then all these points are matched to different points and you get line. Okay, so that's one important notion you need to understand, epipolar line. And the image of the lens center, suppose image of this where the lens is, from the right to the left, this is the image of the right camera in the left, is called epipole. And this epipole in a way is also the intersection of image. This is epipole for the left camera, and this is the epipole of the right camera. As you see, this is the image of this lens here. Now these 2 epipole, EL and ER, they actually intersect the image plane here. So this line will intersect here and here. So these are the epipole. And then the next thing is called epipolar plane. So this is a plane which is formed from this point to this camera center and this camera center. This whole plane is called epipolar plane. So these are the important concepts. Yes?
Just from the image, it's not very clear. So when I go from the camera to the epipole, for example, to the right, it looks like I can keep going with that line and eventually intersect with epipole left.
Yeah.
But that's not necessarily the case, right? Depending on how I have my camera set and what the focal.
Yeah, I mean camera is here. So I have set a camera here. This is the center. So I'm drawing the straight line from here to here.
So I'm making sure that the cameras are set up.
No. I mean, see, the idea is that this is your right camera, yes? And this is my lens, and let's say it's a pinhole, just a one point. So whenever I take a picture, as you know, I take a straight line from that point to draw the straight line from the lens. That's the way light travels. So I draw a straight line from here, connect with this one, and wherever this intersect the image plane, that's its image.
Okay.
Same way, if I take this thing, I draw a straight line from here to here, and it intersect here. So this is the image of this point, which is visible in the right camera. So it's just a straight line. Okay. So those are the notions: the epipole, epipolar line, and epipolar plane. And it's a pretty simple idea, but we are going to use this heavily. So we have two cameras: left camera, right camera. Camera is represented by a lens center, which is CL in left, CR in right, and the point P in 3D is there. We're taking its pictures. These are separated by T. It's a kind of baseline or distance or translation between them, and that's it. So we just connect the point P to the both lens, cameras or lenses. Here the camera is represented just lens. It's a point. Then draw a line here, draw a line here, draw a line here. That's a plane. It's called epipolar line. Then we are saying that if I take a point in left image, it is projected to the line in the right image, because these are the points which are parallel to this point. All these map to a single point. But when I look at from here, these are actually different points in this image. So a point here maps to a line here. Okay? So that's called epipolar line. Then the epipoles are the images of the camera lens of the left in the right, and vice versa. And the line connecting the epipoles intersect these image planes, which is shown here. And the separation between them is translation. So that's the idea. Okay. So once we know that, then we can go in deeper here. And so we'll talk about, we'll say this vector is PL, this vector is PR, and this vector is T. And then since these vectors lie in a plane, so they are coplanar. So we will use this coplanar constraint that if we can take two vectors in a plane and find its cross product, two vectors in a plane, find a cross product, the cross product will always be perpendicular to that plane. You learn this in physics. So that vector, if you find dot product of that vector with any vector in the plane, will be 0, because it's perpendicular. This is, there 90-degree angle, so cosine of 90 is 0. So that's called coplanarity constraint, and we are going to start with that. So we have these vectors, T vector, PL vector, and PL minus T vector. These vectors are in the same plane, epipolar plane. So therefore, we can take a vector T and P, find the cross product, and find a dot product with third vector, PL minus T. This has to be 0 because they're in the same plane. Okay? So also we can relate the PR, which is this vector, in terms of this PL with respect to this coordinate system, because we have the translation between this and this is T. So we take a PL, translate it T, and this possible rotation, apply rotation to that. So we can go from PL to PR like this, which is simple rigid transformation as we've been talking about. So now we have these two things. One is these lie in a plane, and other is that we can relate the PL with PR in terms of rotation matrix and also the translation. Okay? So from here we can simplify this, and we can find bring this on this side, R transpose, and then we have PL minus T, and then we find the transpose of both sides. So this will become transpose, but transpose of this will become PR transpose and R, because when you have two matrices, A, B, transpose of that is B transpose, A transpose. They will change the order, and you can verify that. So now we got this thing, PL minus T transpose is given by PR transpose R, which we can use here to simplify further. So we have a PR transpose R. Instead of this, we get it from here because this is equal to that. Then we have T and cross product of PL. Okay, so we have, so far we are here. Two things, the coplanarity constraint, and then the simple rigid transformation between two of these coordinate system. Then we are going to go through this and express this cross product between T and PL in terms of matrix. That's what we did that before. So we have PR transpose or T cross PL. We will say it is S multiplied by PL. S is the antisymmetric matrix obtained from T vector, and PL is the same thing. And this antisymmetric diagonal, and these are the negative of each other. This is the T vector, which is here. So now we have this PR, which is the 3D location of a point in from right camera, PL, which is 3D location of the same point from the left camera, R is a rotation between these two coordinate system, S represent the translation between these two coordinate system. Okay, so now we have two matrices, the rotation matrix and S matrix, which is actually antisymmetric matrix made out of the translation vector, and the product of these two matrices is called E matrix, which is essential matrix. So you have fundamental, then you have essential. Essential, then you go to fundamental, which is much more important. So it's, product of two matrices is E matrix, essential matrix. So that's up to here what is the Langenhagen came up with this. So this has to be 0, which means what it's saying, if I take a point with respect to left coordinate and take a point with respect to right coordinate, then if I know this R matrix, then multiply these, then it has to be 0 according to this. Geometry is very simple. We just drive it. Okay? So that essential matrix is a product of R, rotation matrix, and S matrix, which is the made out of the translation vector. Okay, so now we will actually go further. From essential matrix we are going to get the fundamental matrix, which is going to relate the points in image in the left image with the point in the right image. Right now essential matrix is relating the 3D coordinates. Here we are going to relate the 2D coordinates. Okay, so now what we do is that when we have a point in 3D, we apply this camera matrix. We talk about M matrix, which contains all those things. So we get this image here in the left camera, and we apply the camera matrix for right camera, which we get image here, XR, which are shown here. And so we have this relationship of the essential matrix, which these are the 3D coordinates here on the right and left. So we're going to use this to come up with better representation so that we don't have to deal with the 3D coordinates. So from here, PL, we can take the inverse of this, bring in on this side. So PL can be written inverse camera matrix minus XL. Similarly, PR can be written inverse camera matrix XR. And so this can also be written as when we take the transpose of this, then this can be written XR transpose and MR minus T. So we can do that. So now we are going to simplify, because the PR transpose from here is XR transpose and MR minus T, which we put here, and PL from here is ML minus inverse XL, which is here. So right now what we have, these are the image coordinate right, image coordinate on the left of the same point, essential matrix, and these are the camera matrices. Okay, now all these are 3 by 3 matrices. Remember, this was 3 by 3 because in the translation and rotation matrix, and these are camera matrix also 3 by 3. So we multiply them and we can just come up with one matrix called F, which is a fundamental matrix. And what we have now is we can take the point in left image, take the corresponding point in right image, then if we know the fundamental matrix, then this has to be 0, and that's a very important result. That is the fundamental matrix between two images. and we just drive its geometry. Okay, so, and you can say that the fundamental matrix is essentially essential matrix multiplied by these camera matrices. Okay, and what this is saying, even though this transformation is 3D, but we have multiplied all these matrices, we come up with one matrix, and it's relating points in image left to the image right. And we don't need to know all the 3D rotation, translation, camera matrix. It's again image based, which is very nice. As we did for the affine, the projective and so on. The only difference here is that here we don't have that we take a point in XL multiplied by fundamental, we get 1 point. We take 1 point, we'll get a line. So this relationship is different, that we take the point and corresponding point, find the product, it has to be 0. So it's a little different because of this 1 point mapping to many points in the other image. Okay, so that is your fundamental matrix, and you know, you should be able to drive this because it's pretty intuitive, pretty simple, be able to do that. So now it's a 3 by 3 matrix, and these are the elements, as you saw, I think in the song they were talking about this. And so given a point in left image, epipolar line right camera, we can find out using, if we know the fundamental matrix. And it is a 3 by 3 matrix with 9 components, but rank of this matrix is 2 because this is a product of the essential matrix and camera matrices. Now essential matrix is a product of rotation matrix, which is rank 3, and the translation matrix with anti-symmetric matrix, and it has rank 2. So therefore, if you take two matrices, multiply together, the rank of the product will be the lower rank of one of the matrices. So that's why it is rank 2. Okay. So now other thing is that it has the 7 degrees of freedom, even though we have 9 unknowns. So one is, this is the like homogeneous system because this is equal to 0. So one degree of freedom we can get rid of like that. The other is that the determinant of this is 0 also, this fundamental matrix, which we'll discuss. So due to that we get 2 less degrees of freedom, so therefore we have 7 degrees of freedom. And in a way it captures that we have 3D rotation, 3 degrees of freedom, 3D translation, we have 3 degrees of freedom in scale. So it's capturing these 7 degrees of freedom between 2 images. So that's fine. So this is the history, as I told you, that Longent, Huygens came up with essential matrix in 81, 92, Hartley and Fojra simultaneously published papers in different conferences about the fundamental matrix, and Zhengzhu Zheng, who's right now in Microsoft, came up with the robust estimation of fundamental matrix. Okay, so so fundamental matrix captures the relation between corresponding points in 2 views, and so we are going to talk about how to compute, given 2 images, how to compute fundamental matrix. Okay, we have derived it now, and we want to know how we can compute. And the way we are going to compute is that we will get image left, image right, and we'll find the points, shift points, for example, shift points here, and find the corresponding points. So this point corresponds to this one, this point corresponds to that one. And those points have to satisfy this fundamental matrix constraint that point here multiplied by f and point there had to be 0. That's what the fundamental matrix is. So we're going to use this property to compute the f. So suppose we look at the point I in the left image, corresponding point right image, so multiply with fundamental matrix, it has to be 0. Okay, so we are going to look at several points like that. So when we multiply this one first, so as you see that this one will come xi prime f11, yi prime f12 and f13, which is this one. Multiply with this will become xi prime f21, yi prime f22, and plus f23, and so on. Then multiply this again with that. So this will be multiplied by xi, yi, and so on. So we'll get like that. So it's one equation. Now in this one equation, we have 12 unknowns, which are shown here. And the other ones are known because xi and yi and xi prime, yi prime are known because we know the points and corresponding point. So like that, we will get this, again, the linear system. We'll get like this. One corresponding will give one equation. We will get lots of equations like that. And f is unknown, so we can write down like that. Again, since it's a homogeneous system, we are going to select one of this element as 1, and then we have to find out the remaining. And so we have this f vector, and then these are the first point, second point, third point, end point, and this is the called measurement matrix. So linear system. So M is 9 by 9 rows and n columns. So rank must be 8 because homogeneous system, it has to be at least 1 less. So let's talk about this Hartley's 8-point algorithm, which is pretty standard, and that says that you need 8-point correspondences to compute the fundamental matrix. Because instead of 9, there are okay. So compute the fundamental matrix F such that this is satisfied. That's what we want to do, because that's our case. Point from the right image, corresponding point from left image, and find the product of this with F shall be 0. So now we have to deal with these practical issues, because we are given these coordinates of the points which you get from SIFT points, and these points have to be normalized, and that will make everything uniform, and we will not have a problem. Otherwise, image size can be different. Some can be 256 by 256, some can be bigger, and there will be a problem. So what we will do, that we will normalize the images by applying some transformation T, and we'll call these transform coordinates head. So xi will map to xi head, and then we can map this back, and so that transformation will normalize these coordinates between 0 and 1. So we'll have some scale, and then also move the origin with the translation. So we will make the centroid of the point, all the points as the origin, and we will normalize these x and y coordinates between 0 and 1. So that is the first step which we'll do in 8-point algorithm. Now then the way we are going to solve this is that A matrix we talk about here, which is our this matrix where we put all these points. Since the rank of this is the 8, even though there are 9 unknowns, we will find the eigenvector corresponding to the smallest eigenvalue of this matrix. So you already know that given a matrix you can find eigenvalues. We did this in the Harris and there was a homework problem and so on. So here that was 2 by 2, but here is a bigger matrix, but that's fine. We can find out the eigenvectors of this, and we will look at the eigenvector which corresponds to smallest eigenvalue and that actually will be the solution for the linear system. And that we can determine, and from there, once we know the solution, that eigenvector we can make as a matrix, because here remember we have done here make this as a vector, but even though these are our vector elements, here we have done here, so this is our matrix and we make the vector, but this was the actually matrix. So once we get that vector, we make it a matrix like this, and this is kind of the first estimation of the fundamental matrix using this idea. Given two images, given the points, given the corresponding points, we put those things in that matrix here, this thing, and before that we normalize them between 0 and 1 and put a center at the origin, which is centroid of these points. Then we take a matrix and find the smallest eigenvector corresponding to the smallest eigenvalue, and that's a solution. So then this is the first step. We get this fundamental matrix. Then we want to normalize it, and which means that we divide by the norm of this matrix, and we talk about how to find the norm. Just divide each element by that, which is easy. And we can use the L1 norm, which is defined like that. So we get that, and then now this is any 3 by 3 matrix, because we haven't imposed this constraint that is a rank deficient matrix, because remember that the translation matrix is the anti-symmetric matrix and it's a rank deficient, and translation matrix was in the E matrix, and it is also an F matrix because we multiply all those. So we want to do that. And how we are going to do it? We'll take this F matrix and we'll find the SVD. We'll factorize this in 3 matrices: U matrix, the diagonal matrix, and the V matrix. So these diagonal elements are the singular value or the inverse of eigenvalues. So we will force it that the third element here will be 0, and that will make this L matrix as a rank deficient. It will decrease its rank, and that's what we want, because fundamental matrix is not any 3 by 3 matrix which we get from that solution, but we want to make sure it is the rank deficient. So we'll artificially make that third element 0, and then multiply the U and V prime with that, and that will be a better matrix. And then we will denormalize, because remember that we converted these coordinates between applying the T transformation to between 0 and 1, and we put a center at origin at the center of the points. So we are going to go back and we'll apply these T matrix to go back the F, and that's the fundamental matrix, 8-point algorithm for fundamental matrix by Hartley. Is a paper in PEMI, and it is pretty important paper. So what we have discussed first is we discuss what is the fundamental matrix and how we derive it using simple geometry. And I think that's not hard, and you should be able to derive it. And main idea was the planar epipolar plane, 3 vectors lying in the same plane. If you take 2 vectors, find a cross product, dot product by other vector, that is 0. So that's the starting point. Then other thing is that I can relate the coordinates with respect to left camera to the right coordinate system by rotation translation, and these 2 cameras are separated by T. So go through all this. Then we say that becomes essential matrix. Then we say we take a picture, and then we define the camera matrices, left, MR, ML, and go through that and come up with F, which is the product of all these matrices. So that is the relationship, that taking a point in the left image, multiply with F, take the corresponding point right, it has to be 0. That's called fundamental matrix, which you should remember. Then given that, then we say, well, now given two images, how we can compute fundamental matrix. That's so useful. And the process is, well, let's look at the definition of fundamental matrix. Say X transpose F, X is equal to 0. So we use that thing. Now, if we know the correspondence of one point, give you one equation, you know the end points in the equations, we put those things with the kind of least square fit, and we have that, you know, the 8 unknowns, so it's 8 points, and then we find the eigenvector corresponding to smallest eigenvalue, and that's what we did. But then we have little other housekeeping to make sure that these coordinates are normalized, so that we don't end up doing different things for different sizes of images. So we normalize these coordinates between 0 and 1, and we put the origin in the center of the points, centroid of the points, and also we made sure that this matrix is rank efficient. So we did the SVD and artificially made the third eigenvalue 0, and then multiply again, and then we did a renormalization applying this transformation T transpose, and we are done. So that's for today. So now after that, then there was a nice paper by Zhengyu Zhang to improve that estimation of the fundamental matrix, and he came up with what is called robust fundamental matrix estimation. So as you can realize that, you know, in the image there can be lots of points, you know. Now the question is which 8 points you want to select using the Hartley's algorithm. It's difficult. So what Zhengyu Zhang did, say, well, let's take an image like this and divide in 8 by 8 cells, okay, that's shown here, a grid. Then what he will do, that randomly select 8 points corresponding from each of the grid points. So you will randomly select 8. There are 64 of those grid cells now. So you randomly select 8, and from each you select 1 point, so that you are selecting these points, you know, whole image, not arbitrarily select the upper half or lower half and so on. So that will be a problem. So you do that, and using those 8 points, you compute fundamentals using the Hartley's algorithm, okay? And now you want to see that how good is that estimation of fundamental matrix. So then you want to look at the error that, as we said, that while you take a point in the second image and multiply by fundamental matrix, you will get a line. And then the corresponding point in the first image should lie on the line. And ideally, you know, practically it won't. So there will be some distance. And that distance is d p1k f p2k. That's a distance, that's the error. And you want to do the same thing. You want to take the point in the first image, apply fundamental matrix, go to the second image, and see how far it is from the line, and take that error. You add up that error, and that is the residual error. Yes?
Those points that we're selecting where we just want to verify our matrix, they're not the same that we used before, right, to calculate it?
Yeah, so yeah, that's a good question. So what we are going to do is essentially you want to use all the points. See, because you only use 8 points to find the fundamental matrix. Now you want to say how good is that fundamental matrix. It has to satisfy all the points which you found. So basically you do this for all the points, and including, of course, it will work for the 8 points which you use, because that's what we use to find the error. So the main thing is that you want to find the error of other points. So one way we just use other points, as you're saying, or use all the points. I think it's better to use the other points as you thought.
So
yes.
Can we use pseudo-inverse?
Yeah, so see the pseudo inverse will come in that instead of finding the eigenvector with the least eigenvalue, as I told you here. So this thing. So this is a linear system, it's a right homogeneous system, and we have been talking about pseudo inverse and so on. So you can do that, or just take this matrix and find the eigen.
Not only the 8 points, if there are more points, dozens of points, we can use this pseudo inverse.
Yeah, so that's the thing. See, the main thing is that when you use pseudo inverse, you use all the points. Then if there are some points which are outliers, the correspondence is wrong, so that will destroy the solution. So what this method is doing, Zhang Yu Zhang, that it will be robust to those outliers. So at a time you select 8 points, and if there are some outliers, wrong correspondences, then the error of that will be much more, and that way you will be able to identify those 8 points you selected. Some of those will be wrong, and you will look at the error, which will be large, and you can identify that. So the main difference, and it's a good question you're asking. So what we have learned so far, just use all the points, and more the better. But now the problem with that is that if there are few points which are outlier, which are wrong, but you don't know, that will destroy the whole thing.
Why not use Renset?
Huh?
Renset.
Yeah, so this is kind of RenSec. That's another good point. So you are getting there. So RenSec is a way to deal with. So you randomly select 2 points. So this is in a way doing that.
Yes,
This is similar. Okay, good. So we are making progress. So this way it will find the error of every 8 point selection you got. You get a fundamental matrix. You want to look at the error of remaining points. And this is symmetric error. The point here, go to the line, what's the error? Point here, go to the line, what's the error? Add it up. And so from all those trials, you will pick the best F fundamental matrix, which has the smallest error, but the smallest error has to be some threshold. And then using that, you will remove the outliers. If the some fundamental metrics have very large error, then that will give you the outliers, and you can get rid of those. And then now you have selected from these many different fundamental matrices. You select the best, which has the least error, is this one, and then you have, using that, you have, because for each of the point the error, because this is computed for each of the point. So you have lots of error for particular fundamental matrix. You select which has the least error. So using that, you remove the outliers, which has a larger error, and then remaining points you can use to do another fit to find the final fundamental matrix. And there you can use the weighted least square fits. You can assign the weight inversely proportional to the error which you found. So those are the steps which you are about. Yeah.
When I'm determining my outliers by checking if R sub k is greater than the threshold, does that mean that I will discard all the 8 points that I have selected to create the fundamental matrix?
No. So see that this is computed for the other points. So you have computed some fundamental matrix, yes? Using that fundamental matrix, you compute the error of all remaining points. You have lots of errors of points. So then you add up all the errors for this fundamental matrix, now, and pick the one which has the least error. That's first step. Now you have that. That's well, we are going to use that fundamental matrix. Now using that fundamental matrix, then you identify some point which has a very large error, because you will get an error for each of the points. This Ri is for each of the points, ith point. So you pick those and you remove those. Okay? So those are the outliers, and which means their correspondence was wrong. So you remove those. Your remaining one, you then use those to find the final one. So it's very nice, very interesting, and that's a way to deal with the outliers. And this is basically RANSEC. This is randomly sampling and coming with a consensus, and so on. Here we need 8, and if you remember, we did in straight line we needed 2, so we're selecting 2, and that's the idea. Okay, so that's that, and so let's then now finish this up. So now we can use this fundamental matrix in these epipolar lines. So this is one image, this is second image. They are taking of the same scene from different viewpoint. So if I look at this point, corresponding to this point, this is the epipolar line. So this point matches to the line. So as you were asking earlier, that when we find the match of the points, of course this point matches with this. That's what we are going to do using SIFT and so on. But now once we compute the fundamental matrix, then we know corresponding to this point, what is the epipolar line, which is this one. And match of this should lie on this line. Okay? So the similarly, match of this point, should lie on this line. So these are called epipolar lines, okay, as we showed you in the beginning of this thing. So, and this is another image, it's a drastically changed. Still we can compute the epipolar lines. So this is the point and this is corresponding to the epipolar line. So this is very nice. The more examples and so on. So these are your SIFT points, and then you find the matches using SIFT descriptor and so on. So about this point, you will say where does it match in this image. Of course you are going to look at around the same neighborhood, same location, and say, well, this matches best with this one. So this is a match. So this is xi, yi, this is xi prime, yi prime. Similarly, you look at another one, find the matches. Giving the matches, get the fundamental matrix, then getting fundamental matrix, you can find epipolar lines. Yes?
The correct point, though,
huh?
There wasn't a correct match, though.
What do you mean?
It has to be lower.
This one?
Oh, you were matching that.
Yeah. Okay. So what is this one? This is Empire State Building. Anybody going to New York?
No.
Oh, you should. Okay. So let's let's do the stereo. So one application of this is in stereo, that you have two images and you are looking at the point in 3D, and this is first camera, this is second camera, left and right camera, and image of this point in the left camera will form here, image of this point will form here, and these cameras are separated by B, which is the baseline, and the distance of this point in 3D is Z, and this distance from here to here, from image plane to the lens, is F, which is the focal length. So using these two triangles, there's one triangle here and smaller triangle here, we can find out a depth. And because the Z plus F upon Z, so there's a big triangle and then this is a small triangle, and then x1 plus B plus x2, which is for the big triangle, the base, and then smaller triangle B, they have to be equal, they are equivalent triangle. So using that we can find out the Z is equal FB x1 plus x2. So x1 and x2 is called disparity, the distance from the left image compared to right image. B is called baseline, the distance between cameras. F is a focal length. So it depends, the disparity depends on the depth. Depth depends on disparity in inversely proportional. If the disparity is large, depth is small. Disparity is small, then the depth is large. So here's examples of stereo pair. These are two images, and using this kind of method you can compute the depth, which is shown here. This is pair and in computing depth, then you can visualize this from different viewpoint, which is shown here, and like that. So fundamental matrix is used to rectify these images. So image can be taken like this and taken like that, so you can rectify. Now you can just go to find the match of this. You will just go in the same row in the next image, find that, and that will give you a disparity, and that's can you use for stereo. So let's look at how we can find the match. So these are two images, and let's say they are rectified, and we have one on the left, which is shown in the red box. We want to go to the right image, exactly same row. We want to find where does this match. Okay, so and we can look at different possibilities, say, well, does it match here, does it match here, does it match here, and whichever give you the least error, our best match is the selection, and depending on how far you want to move this way or this way, disparity will change, and that's the plot here. So now to find the match of a page in left to the right, and we can do using correlation, and that's the one of the first method for the stereo. So so now how do we do correlation? So we will take page in the left image, corresponding page in the right image. We'll do sum of square differences as we did before in the optical flow and so on, and find the difference, square it, sum it up for all the pixels. It's a 2D window, and if it matches, it has to be, if it's exactly same, it will be 0, but if it matches, small number. So this is one way of correlation, sum of square difference. You can, instead of squaring, you can look at absolute difference. You can multiply, this is a real correlation, multiplication as we talk about. You can normalize it, do this correlation and then divide by this thing. And then there's another normalized correlation where you look at the mean and the standard deviation of a page here, page there. There's a different measure to match a page from here to there. And so that is, you can basically do a stereo like that. Take two images, and assuming they are rectified, then you can just take a page and find the match, and you can find disparity, you can find a depth map like that. So there are many, many stereo algorithms, because in general, it's not easy to find the match because there's a lot of ambiguity. And so one of the earliest method, which was very popular, is called Bernard's stereo method. So we're going to talk about, it's a very simple idea. So the idea is that we want to find the match so that a page in the left should have, the brightness of the page in the left should have same brightness in the right. It's a brightness constraint which we use in optical flow also. But in addition to that, the disparity should be smooth over image. And so very similar as you remember in optical flow. We say brightness has to be similar, it has to be constant, and also the motion has to be smooth. So that's similar thing they use here. And this is expressed by this. So this is the brightness similarity. So we are looking at the left image, different pixel. And this is the right image with the disparity, because disparity will be shift in x direction. So that is the shift in x direction, and we want to find this. And so this is simple, your absolute difference, sum of square difference, and this is the square window. So we have these, right now we are doing 3 by 3 window, but you can do any much. So that's the first constraint, similarity, similar intensity. Second constraint, we are saying the disparity map which we'll find has to be smooth, which means the gradient of that has to be small. Okay, so that is the lambda, the combine with that. So that's the function they use, and this is the definition of the disparity, which is just finite derivative. This is a finite difference. Okay, so that's very simple, and now, so that in a way is energy. This, we want to minimize this energy E. We want to find the disparity D, which is a disparity map for every pixel. We want to come up with a number, okay, and such that this is minimized in this definition. So now the question is, how do we do it? Okay, now one is we can do brute force source. We say, well, given these two images, the maximum disparity range is 10 pixels. So we can, look at, well, how about disparity 1, how good is disparity 2, how good is, and so on. So then if we have 128 by 128 image and 10 possible disparity, so we will have lots of combination, which will be here, which is 10 to the power 16,000, possible disparity, which will be many combinations. You have to check what is disparity. So there will be a lot. So this is where we can use some intelligent way to minimize this energy or function or cost, and Bernard used this what is called simulated annealing. So simulated annealing is a process in materials. When they want to make this good materials, they will heat up very high temperature, then will lower down temperature slowly. When you heat up, there'll be lots of these molecules, atoms will have lots of movement and so on. So then when you slowly lower down, then they'll become stable and you'll get a very nice material. So that's what we are going to do here. And so we don't know for each pixel what is a disparity. So we just randomly select a disparity, okay? And then we select a high temperature. So then we select another disparity randomly. So we'll compute the error, the energy between the first disparity, and second state. Okay, what's the difference? Energy went down or energy went up? Both are random, no? So we don't know. So we look at the difference, and if the energy went down, then we are going to take the next state, the S prime, which is the second state, which is a basic disparity. If energy did not go down, so we are going to generate this P, which will be exponential minus delta E divided by temperature, T. So depending on how much is the error, the delta E, and the temperature at the beginning, the temperature will be very high. We'll get some probability that with what probability we should take the state, even though it is energy has gone up, or not take it. So that's where randomness is coming up. So so that what that will do is that if you have a function which is a local minimum, now this is where I need a marker. Anybody has marker, or do I have here picture? No, I don't have. Anybody has marker? So yeah, okay, very good. You don't have, you have. Okay, great. Thank you. Your whole page. Come, bring every day. Bring this one, please. Okay. So there is a function. Okay. And this function is like this and like this. Let's make it like this. Okay. This is a function, and what we want to find out. We want to find out the global minimum of this function, okay? So if you look at where is the global minimum of this, where is the point where is the least? This is the point, yes? Here. Now, there are many local minimum. So suppose this is a minimum, this is a minimum, this is minimum, this is minimum. So one is a global minimum, which is this one, and these are the local minimum. So always whenever you want to minimize, there's a problem, get caught in the local minimum, and you want to get out of that. Now, so what this is doing, that well, we'll come up, say, well, oh, we took at this state, the next state, this one, this is energy is lower, we can just stop. But this will be wrong, because local minimum is here. So randomly we'll jump out, we'll take the wrong step, and we will go up, we will not, So that will give you will end up with this thing. And these jumps we will do will depend. In the beginning we'll do lots of jumps because temperature is very high, and then we slow down and we'll do less jumps, and that is called simulated annealing. And so again, very, very simple, intuitive method to do that, but that works. Yes. Yeah. So temperature is this is a function here. So we will generate the. So we will know what is the change in the energy, delta E. Yes, this is the delta E, and energy we have defined like this. As you remember that we have this is our energy, which is the difference between left and right, the disparity, and the smoothness, which is the gradient. You understand energy, yes? If you know the disparity, you can compute energy. So we have one disparity, which is S, we have energy. We have another disparity, S prime, we have energy. We can find a difference, which is delta E, yes? That's energy difference. Now, depending on the delta E, we will generate this P, where delta E we know, we can put a number there, and T is a high temperature, high value. And we put in E to the power minus delta E upon T, we'll get some number. Okay? So that is the temperature there, just symbolically, because this is using the simulated annealing. And we are doing this to find this number P. And what we are going to do, that now we got a P, and we generate random number between 0 and 1. If this random number X is less than P, then we will take that state. If it is not, we will not take it. So that's the algorithm. So temperature is here to compute the P. And we know the delta T, we have a started temperature, and there's a whole schedule that you start with 100, then every time you reduce by 10% and so on. There's all details. Okay? So, yes?
The function of temperature can be, right?
Huh?
The function of temperature, it can be linear, exponential?
No, function, how you change it? Yeah, how you change it. So there's a whole schedule that, see, you start with 100, then every time you reduce by 10% or something, there's all, those things.
Different methods for that.
Yeah. So, but conceptually that's what's happening, that if the temperature is high, there's a lot of movement, then you'll take these wrong state quite often. But when the temperature is low, then you will take with less probability. So that's the idea. Okay? So we do that, and if no decrease in several iteration, lower temperature, and then you keep doing that. So that's, if you do that, then you can get the depth map like this, about braid, toy, apple. And this is left domain, right domain, so depth map, and this is another depth map. And there is a whole data set from Tsukuba University in Japan. Who has been to Japan? Nobody. Actually, I was there. You have been to Japan. I have been to Tsukuba. Where are you from? Which city in Tsukuba? Yeah.
Where I'm from?
You're not from Japan. Which city?
Tokyo.
Tokyo, okay. It's about 1 hour train drive from Tokyo to Tsukuba. I went there. It's very, very hot in summer. Okay, so this is the scene, and they have this ground truth for depth map. As you see, the lamp is, a different distance than compared to this camera and so on. So these are disparity, the depths, which is shown here. So there are this finding the right depth map efficiently and correctly. There's a whole area of research, and this is if you do the simple window-based correlation, this is the depth map you will get. It's the ground truth, as you see, the big difference, and then this is the state-of-art method, which gives you very nice compared to this one. It's a lot of errors, and this is very similar to this one, and so there's a whole data set there. And there are lots of application of stereo. You can generate a different view of the scene. Suppose you have an image here. If you have stereo, get a depth map. You can then take a picture from the other side. This is the view morphing. You get these two images. You can generate a third one, and you can do virtual reality. You can put objects there, and so on. So this is from Zaleski's book. Okay, so you can look at this material for reading, and it's covered nicely in my book and also Zaleski's chapter 11. So that's it.